Hello everyone, and welcome to the ME 296 lecture on semiconductors. We're going to cover the physics behind semiconductors, what happens when you place two of them next to each other, and our first semiconductor device, the diode. So, in between insulators and conductors is a group of materials called semiconductors. And these materials have properties that are somewhat in between those of insulators and conductors. They do conduct electrons, but not as many as conductors. And they do somewhat slow current flow, but not as much as an insulator. The amount of electrons that are allowed to move through them is highly dependent on the amount of energy available in the environment. And the reason for this is what's called the energy gap between the valence band and the conduction band. So on the right side of the screen, we have a plot representative of the potential energy of our atom. And the plot is essentially a representation of the amount of attraction the nucleus has on the electron, where negative values are attractive and positive are repulsive. If an electron has not so much energy on its own, it's trapped at the distance with the most attraction to the nucleus. It doesn't have enough energy on its own to overcome the pull of the nucleus and has to stay where it's put. That's the orange electron on the plot. The blue electron, however, does have enough energy on its own to overcome the attraction of the nucleus and can go wherever it wants. It has enough thermal, kinetic, applied electromagnetic energy, whatever, to overcome the pull on the nucleus. And the energy that's required to overcome the pull of the nucleus is called the gap energy. Insulators have a very large gap energy. The amount of energy that an electron would need to overcome the pull of the nucleus in an insulator is so high that it rarely ever happens. And conductors have a gap energy which is very small. We can often just simply make it a couple of degrees warmer, and then that's enough to free a whole bunch of electrons. Semiconductors have a band gap somewhere in the middle. The most common semiconductors that are used are silicon and germanium, which have band gaps of 1.14 electron volts and 0.67 electron volts respectively. So this tells us that the materials we are using affect the amount of free electrons for a given energy. So if we have energy available in our system, that's going to be applied to our electrons in our system, and some of them are going to get freed and some of them are not, dependent on that band gap energy. A material with a lower gap energy would see a greater amount of freed electrons, and therefore we have potential for a much higher current for some given applied energy. So in addition to the natural semiconductors, it's very common to dope materials to adjust the amount of electrons. And this basically just means that when you're growing your semiconductor crystal, you introduce another element in specific amounts to get the results that you want. And broadly speaking, there are two kinds of doping, p-type and n-type. P-type doping stands for positive doping. The element introduced has spots available for additional electrons to be bound. It's sometimes conceptually useful to think of these places that are missing the electrons where we can bind new ones as a kind of particle which is called a hole, which has a positive charge. Now these are pseudo-particles, they're not real, but they do have properties that are very similar to real particles. Think of bubbles in soda. There's not really soda there. It's a place where soda is not, but they still move around like they were a real particle. On the other hand, n-type doping, or negative doping, introduces elements which have extra electrons to donate, and this can increase the number of free electrons at a given applied energy. And almost all of our semiconductor devices are created by layering these two types of doped semiconductors on top of each other in some layering fashion. So what does that look like when they're in layer, which is where all the interesting stuff happens. Here we have a p-type and an n-type abutting each other. And just by being attached, the extra electrons on the n-doped side want to cross over and fill the holes on the p-doped side. And this starts to happen. But it happens at the interface boundary first, and then slowly marches onto either side through like a method similar to diffusion. But remember that the doping agents are atoms, which were originally neutral. So when that extra electron leaves our n-dope atom, that atom becomes a positive ion. And when that electron reaches the p-dope atom, that atom becomes a negative ion. And since this happens at the boundary first, we have a region on the p-doped side that's becoming negative, and a region on the n-doped side that's becoming positive. And that negative region, as it grows, starts trying to repel electrons trying to cross it. And as it grows, eventually it's going to stop the diffusion of additional electrons because there'll be so much negative energy in between the electron and where it wants to be that it's just going to keep that electron over on the side that it started on. And a very similar thing happens on the positive side. If we think of the holes as particles, they're trying to diffuse across and fill the atoms on the other side, but we have a positive region that kind of stops that from happening. Eventually, we're going to reach an equilibrium, and the region at the junction effectively stops the flow of electrons from one side to the next. This region is called the depletion region since the electrons in this area have all left. They've all moved on. And this equilibrium region creates a difference in the energies on either side of the junction. The n-doped side have a bunch of electrons left that could move, but the conduction band on the p-doped side is higher than the n-doped side. And all the electrons with enough energy have already crossed over, so we've stopped our flow of current without adding more energy into it. You can see from the plot on the bottom that the conduction band and the valence band switch kind of magnitudes at the boundary and the interface region. So that's cool. We have two things side by side and we had some electron flow across them, but now they've stopped. So what do we do to get it moving again? Because circuits are all about things moving. So the process is as follows. We apply energy to the n-doped side, and the energy of the electrons increase. And if enough energy is applied, electrons are going to enter the conduction band. These newly energized electrons are attracted to the other side of the junction, and now they have enough energy to make a cross due to that newly applied energy. They're going to combine with the available holes, and they're going to negate their own electric charge, which would repel more electrons from coming over. So if we have the semiconductors attached to some kind of circuit, which siphons electrons from the p-type and supplies electrons to the n-type, we can now have a consistent flow of electrons across the semiconductor as long as we maintain that additional energy. However, if we apply energy to the p-type side, not too much happens. The electrons aren't trying to go the other way. They're trying to go to where they already are. So adding more energy there on the p-type doesn't do anything. And this gives rise to two kinds of operations as applied to this kind of junction. And we call these types of operation modes or operational biases. If we're supplying the energy to our electrons through an electrical field, such as we might in a circuit, if we apply the electrical field so that the positive end is on the p-doped side, we result in a current or electron flow because things are moving the way they want to. And this is called forward bias because things are allowed to progress forward. But if we flip it and apply the electric field so the positive side is on the n-doped side, this is a reverse bias. We don't want to, the electrons aren't going to want to move anywhere. So nothing happens, no current. And this has some really serious applications in circuit design and leads us to our first semiconductor device, the diode. Diodes are a simple p-n junction, just like what we've been talking about, p-type, n-type junction, and it's got two leads attached to it. One lead is attached to the n and the other on the p. In the ideal case, a diode will only allow current to flow in the direction of the arrow. If we try to apply current in the other direction, it blocks the current and acts as a brake. If the current is flowing in the direction of the arrow, the diode is instead a short. In real life, there are some requirements though. So remember that energy difference between the two sides, or that band gap energy? The applied current must have enough energy to overcome this, and when the electron crosses that band gap, it loses that energy to the band gap effectively. So in silicon diodes, you need 0.7 volts to overcome that band gap energy. In germanium, it's only 0.3. But if you apply 1 volt across either end of the diode in forward bias, if you start with 1, the other end is going to come out with 0.3 in a silicon diode because you needed that 0.7 to overcome that band gap energy. So some more real life attributes that are important is the amount of current flow and the breakdown voltage. So the Shockley diode equation describes the flow of current across a diode as a function of the applied voltage. For the most part, we're not going to worry about this. The important part is that current is proportional to applied voltage. So in order to ensure consistent behavior, we need to apply enough voltage to make sure that we're at our maximum current flow so that we don't have unstable oscillations in our current flow. And the breakdown voltage is the energy required to break the diode. If we apply our electrical field in a reverse bias, we can actually apply enough energy to strip the atoms of all their electrons and just destroy the whole thing altogether. And this is going to remove all the special properties of the diode, and it's just broken. So when designing circuits with diodes, it's important to regulate the voltage applied in both directions. We don't want them to break, and we want to ensure that current is flowing in a stable manner. I'll go over how to be doing this in a future video. So let's see one of the really neat features that also comes across from diodes, and it is an LED. So the LED is very similar to a regular diode. The biggest difference is that the band gap energy corresponds to a specific wavelength of light. Remember that light is a form of electromagnetic energy where the energy is equal to h times the frequency, where h is Boltzmann's constant. If we carefully construct our diode, we can ensure that as some electrons cross the junction and drop into the valence band on the other side, the energy that they no longer need is then converted into light with that specific energy. And because that energy is associated with a specific frequency, we get a specific color for that. And there are tons of applications for semiconductors beyond this, but this is the most common one that everyone should be familiar with, and it's the one we'll be using first. Such as you can make a thermistor or a device that changes the conduction across it based on the temperature of your system. Or you can make a reverse LED where if you shine light on it, the energy from the light actually gives you the required energy to jump over the band gap and start current flowing. This is how you can make some kinds of sensors. Right, but that's everything for this particular video. We're going to go over the transistor next, and then a couple of examples. Right, thanks for watching.